Hi, this is Dr. John Bergduff. This video is basically going to be a very conceptual video. We're going to do something we're actually not ever really going to do in real life. We're going to look at a function that we already know and a graph that we already have and use those two facts to factor the polynomial. Now, this is exactly the opposite of what we ordinarily would do. What we would usually do is start with the polynomial, figure out how to factor it using the rational zeros theorem and synthetic division and so forth. And then looking at the factored form of the function, we would draw the graph. Now we're going to look at the graph and figure out the factored form. So basically, it's not something you're ever going to really do in real life, but it does nail home some of the conceptual ideas about factors, zeros, and shapes of polynomial functions. So I want to look at the graph and first of all just see if it makes some sense, and then use what we know about zeros and factors, and mainly the factor theorem, to see if we really can accomplish what they're asking for. So let's look at the leading term. Notice that the leading term has an x to the fifth in it. The leading term of the polynomial function gives the end behavior or overall structure of the graph. If we remember what y equal x to the fifth looks like, it would be basically sort of a wiggle shape going from lower left to upper right. And more or less the end behavior of this graph does fit that. So that makes sense at least. Also, looking at the leading coefficient, the leading term, because it is an x to the fifth term, that will tell me that the polynomial would have to factor into 5 factors. So eventually we're going to be multiplying 5 linear factors together. Now, we also know from the factor theorem that the zeros of the polynomial correspond to factors of the polynomial as well. So let's look at where the zeros are and see what they tell us. This polynomial, for one thing, has a 0 at -3. And the factor theorem tells me that if -3 is a 0, then x plus 3 must be a factor. So one of the factors of this polynomial must be x plus 3. Let's look at the other zeros. Here's a 0 at -1. That means that x plus 1 has to be a factor, so one of the factors has to be x plus 1. And finally, because there's also a 0 at +1, a 0 of 1 would correspond to a factor of x minus 1. So the factorization of this polynomial would have to at least begin with this. Now, notice that this only gives me 3 factors, and I've already said there ought to be 5. Let's look carefully at the behavior of the graph at each 0. Notice, for example, that at -3, the graph touches the x-axis like a parabola. When that happens, that tells me that the power on the factor must be even. So let's conjecture, just to start with, and we'll see how this nails home in a minute, that the power on the x plus 3 must be x plus 3 squared to get that general shape. Let's look at the other zeros. Look at what happens at -1. At this point, the graph crosses through the axis like a line, and that tells me that the power on that factor must be odd. Let's leave that as a 1, just for now. And finally, looking at the last 0 at +1, the graph again there touches the axis like a parabola, telling me that the power on that last factor must also be even. And you notice that I keep saying even and odd, but I put specifically 2 and 1. And you might wonder why that is. Why couldn't this power, for example, have been a 4? Or this one have been a 3? Well, actually, this all boils down to the fact that I know that I have to have 5 factors because of the x to the fifth in the first term. And if I used any exponents greater than this, I'd end up with more than 5 factors. As it is, there are 2 factors here repeated, 1 factor here, 2 factors there repeated, for a total of 5. So that tells me that this polynomial must factor as x plus 3 squared times x plus 1 times x minus 1 squared.